In today's video, I'm going through exercise 1.32 from the Art of Electronics. In this exercise, we need to show using a phasor diagram that the response of a high-pass RC filter is equal to V out equals V in R over the square root of R squared plus 1 over omega squared C squared. So the equation that you can see on the screen now. So first of all, I'll quickly show you what a high-pass RC filter is, and then show you what phasor diagrams are. There are tons and tons of videos on high-pass filters and phasor diagrams on YouTube. So if you want to learn more about high-pass filters or phasor diagrams, please watch that before watching this. But I will quickly cover them in this video as well. So a high-pass filter, a single section RC high-pass filter, which is what I've shown on the screen here. We have basically our input voltage that's coming in from this direction, and our output voltage is basically connected here. So this essentially is where we would connect our load. That might be a input to an ADC or a secondary filter or anything. Now, the configuration of an high-pass RC filter is such that we have the series component as the capacitor and then the parallel component as the resistor. So you can see clearly from here that the output is equal to the voltage across the resistor. Basically, the impedance of this capacitor changes with frequency, giving us what we see on the right-hand side. Obviously, this is an ideal response. You can see below some cutoff frequency over here, which would be typically denoted as FC. We would block everything that's going through. And then after the cutoff frequency, the filter would pass all the signal. So the gain on this side over here would typically be 1, and then this line would be 0 here. Obviously, this is an ideal filter. A real filter would probably look a lot closer to a curve that looks like what I'm showing on the screen right now. Anyway, if you want to learn more about high-pass RC filters, obviously I've got videos on there as well, and there are a lot of videos on YouTube that you can follow. Now, just to quickly explain what phasor diagrams are. They are basically a graphical method that help to understand reactive circuits. So in a series RC circuit, like I showed you with the high-pass RC filter, the axis, basically the axis being this one and this one, so this axis would show you the real part, and then this axis would show you the imaginary part of the equation. So obviously that would be covered by the capacitance, and that would be covered by the resistance. In our case, obviously, the output voltage is proportional to the voltage across the resistor. The angle over here would show you the phase shift. For step number 1, to answer this question, you should try and calculate the total impedance of this circuit. So from Kirchhoff's voltage law, we know that V in is equal to VC plus VR, ignoring any loads on this side. And also that V out is equal to VR, because obviously that's the same node. And using Ohm's law, we can basically write down V in as equal to the current through this circuit multiplied by the impedance of the circuit. So that's the total impedance of the circuit. And also using Ohm's law, we know that the voltage of the resistor is equal to the current through the resistor multiplied by the resistance. We can also write down the voltage of the capacitor, which obviously we've covered in our previous questions, and that's been covered in the book as well. The capacitance voltage is equal to minus j omega c times by the current through it, or 1 over j omega c. So plotting all of these into this equation over here, we get the following equation. Basically, Iz is equal to IR minus j omega c I. Now, if we factorize this out, basically, so we've got I on this side and take the I out from both of these, we end up with this equation here. So Iz is equal to I, and in brackets we have R minus j omega c. Now, if we take the I over to the other side, we can cancel the two I's out, and we end up with J equals R minus j omega c. So the total impedance of this circuit, without kind of going into this right now, is R minus j omega c. So just bringing the final equation to this slide over here. So we've got the total impedance is equal to R minus j omega c, we can start to populate our phasor diagram as well. So obviously the real part is on this axis, so that's R if you want to look at the impedance, and the imaginary part is on this axis, which obviously we have as xc. To calculate the total impedance, which is basically represented by this line or the hypotenuse, we can use this equation over here. So a squared is equal to b squared plus c squared. So our b is obviously r and our c is equal to xc. So putting those numbers in, we get our total impedance squared is equal to r squared plus xc squared. And then taking the square on the other side and turning it into square root, obviously, we get total impedance is equal to the square root of r squared plus xc squared. And now filling this out from our previous equation of 1 over j omega c, we can basically write out the total impedance is equal to the square root of r squared plus 1 over omega squared c squared. Now bringing that last equation back over here to the next slide, we can basically look at the output voltage, which is equal to the voltage across the resistor. If you know your potential dividers, the output voltage obviously is equal to the input voltage multiplied by R divided by the total impedance of the circuit. So we have VR is equal to Vin multiplied by R over the total impedance. So if we just populate this back into this equation, we get to V out or VR is equal to Vin multiplied by R over the square root of R squared plus 1 over omega squared c squared. So you can see that we have arrived at the solution that the question has asked us at the beginning. Thank you for watching today. If you have any questions, please let me know in the comment section below.